Hi folks, welcome back to Physics with Captain Rod. I'm making this video to help you folks out with Unit 1, Problems 12, 13, and 14 here in Physics 109. So in number 12 is basically just a conceptual question here. I'm just going to talk a little bit about how to answer it. What you're looking at is a position graph. Looks something like this. And then you have to choose from 4 velocity graphs. Keep in mind that velocity is delta x over delta t. And it's very important that you remember that, all right, change in something over change in something. This thing is a slope, but it's very important to know slope of what type of graph. Well, it's a slope of position against time graph. And although this says d and not x, that's basically what they mean. This is a position graph. So as far as this graph is concerned, the velocity is given by the slope. So ask yourself, in this region, what do I know about the slope? Can I calculate a value, or do I know a value? In this region, do the same thing. You can probably answer this question without actually doing any calculations. If you ask yourself, okay, in here is the slope positive, negative, or 0? In this region, is the slope positive, negative, or 0? Positive, negative, or 0? Positive, negative, or 0? Positive, negative, or 0? And just look for the graphs below that and match up with that. Okay? That's probably enough on that one. Let's talk about 13. A rock is dropped off the side of a bridge and it hits the water 6.3 seconds later. Now that one, here's the first problem here that I would call, really more of an actual physics problem. So I'm going to chat a bit more about how to do this one. Okay, a rock is dropped off a bridge. I'm going to start with a picture that kind of describes this problem here. So we've got, maybe some sort of bridge. I'll just maybe do this, which is supported on the ends. Maybe down here there's some sort of lake. I don't know. Presumably a person dropped that rock. So I don't remember if you folks have seen a video that I made about motion diagrams, but I'm going to go ahead and draw the motion diagram for the rock. Motion diagrams are just those like snapshots in time. I always think of a digital camera. Click, 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 taking pictures. And then you superimpose all of the pictures. As the rock falls, it's going to be speeding up due to gravitational acceleration. And that's why the distance between clicks, like the distance from here to here, and then the distance from here to here, and then the distance from here to here. Because the rock is speeding up, that's why that distance is getting larger and larger and larger. So in my picture here, I'm actually trying to remind myself that this rock's going faster and faster and faster via this motion diagram. If I were to draw velocity vectors, very quickly here, or right after the rock is drawn or dropped, the velocity vectors are very small. But as the rock picks up speed, that means you're moving at higher velocity. So we would represent that with larger vectors. Okay. How do we actually solve the problem? So one of the videos that I had you watch was basically how to use velocity graphs to solve problems like this. I'm going to go ahead and start with a sketch here, velocity against time. And that's what you should do as well. Now remember, velocity is how fast and in what direction is the rock going, or whatever particle we're talking about. This rock was dropped. So right at the instant it was let go, it's really not moving yet. So its velocity is basically 0. So I'm going to put a point on the graph for that. Now, when the rock hits the water, it's going some speed. I don't know that. The delta t is given in the problem. In my example, it says 6.3 seconds later. So that's my delta t, 6.3 seconds later. You're going to have some other value, no doubt. So that means, okay, if I go over here 6.3 seconds, however fast the rock is going is my velocity. Now I don't know a value, but it has to be something. I'm just going to come up here and put a value, and I'm going to call that value v and put an f on it for v final. So what I'm doing here is I'm assigning an unknown to that unknown speed. Okay. Now, hopefully you've seen my video about gravitational acceleration. The acceleration of this rock is roughly constant, meaning not changing, and it's down at about 9.8 meters per second per second. If the acceleration is not changing, that means your velocity graph is linear. So I'm going to connect these with a line. And now the question is, how do we use this graph to solve this problem? Now these graphs have two important properties about them: slope and area. And these are the two properties that we can use to kind of calculate or analyze the motion of the rock. So let's talk about slope first. Remember, slope is rise over run. This would be the rise. That's what I called V final. This would be the run. In my example, that's 6.3 seconds. So the slope in this example, right, is going to be rise, which is what I'm calling V final, over run, 6.3 seconds. And I know that that slope is the acceleration of the rock, which is 9.8 meter per second per second. I like to write it like this: meter per second, because the rock is accelerating gravitationally. Right? This can be solved for the V final. Once you have a V final, you now know that distance on the graph. The distance that the rock fell is a displacement, or I usually call that a delta x in most of these videos. In this example, that's going to be this distance right here. That distance we can get from this area here. And if you're not familiar with that, go back and watch my video on how to find displacement from a velocity graph. It's area under the curve. And this is a triangular area. So 1/2 base times height will give you the displacement. Some things to keep in mind in this problem. Look at how useful the velocity graph is for analyzing it. And we're using the slope is equal to the acceleration, and the displacement is the change in position. So I hope that this helps with number 13 here. Let's chat about 14. And I'm going to go ahead and just get myself a new picture here. Let's see, during takeoff, a plane goes from 0 to 48 meter per second in 7 seconds. So I'm going to take a moment here and get myself a picture of a plane here. I got all sorts of cool pictures I use for these videos. Somewhere here I thought I had a plane. What, did I miss it? Oh, there it is. Good enough. Maybe I'll start with this. It's a Messerschmitt, I believe. Oops, I'm going to shrink that plane down. Wouldn't need quite that large. Okay, so this plane starts from rest, but I do know it's accelerating. So what I'm going to do is I'm going to modify my picture to show that. All right, so maybe a time frame goes by and the plane has moved maybe this far. And then another time frame goes by and the plane moves a bit further, because remember, this car is accelerating. And then another time frame goes by and the plane's moving a bit further, and so forth. So again, these distances are what we call displacements, or delta x is what these are in the equations here, right? And here's another delta x, right? And here's another delta x. And delta x is just a change in position. If I were to draw a velocity graph for the plane, now why the velocity graph? Velocity graphs are very useful for analyzing the motion of an object that's accelerating. So velocity against time, right? At t equals 0, that's when the plane first starts. It's not really moving yet, so the first point might look something like this. In fact, it says in the problem, it goes from 0 to 48 meter per second in 7 seconds. So 0 to 48 meter per second in 7 seconds. Your problem, no doubt, will have different numbers. So at 0 seconds, the plane is going 0 mile per hour in my example. In 7 seconds, it's going 48 meter per second. So on this picture, I'm going to come over here and just put a 7 seconds. And then I'm going to come up here and put a dot. This is now the 48 meter per second. Now you'll notice that I basically put this dot anywhere I want. When you're drawing a graph like that, a quick sketch, it's perfectly acceptable to do that. Just keep in mind that you've now set a scale. If this is 48 meter per second, then 100 meter per second would be maybe about here, and 24 would be about here, and so forth. And again, I've set a scale here too. If I put my 7 seconds here, 3.5 would be about here, and 14 maybe about here, and so forth. Right? So to draw your graph, put a couple points in that we know. I'm getting that from the information in the problem. We're going to assume linear acceleration, which means this is going to be a line. I'm sorry, we're going to be assuming constant acceleration, which means this will be a line. And then we should be able to write a pair of equations using slope and area. We don't know the acceleration, but it's equal to the slope of this line. So rise over run will get you the acceleration. And then this area here will get you the total delta x from here all the way to here. And those are probably in that question. So, all right, that's pretty much enough on that. Let's see, part A says how to find the acceleration, that's the slope. Part C, the how far did it travel, that's the total area. Part B says how fast is it going after 3 seconds. So let me go back and talk about B. Well, 3 seconds on the graph might be about here, and we'd be about here on this curve. So what you're going to do to answer that question is just use slope again. This distance is some speed, which we don't know. The slope is going to be that distance over 3, and it's going to equal the acceleration that you found in part A. So that's how you'll answer that. So anyway, this video is getting a little long. I'm going to stop that right there. I hope this helps you get your homework done. You're going to take a quiz next week. These are the types of problems and questions that are going to be on that quiz. You'll definitely have one like this one, no doubt. But no more complicated than that. I'll make another video in by itself to kind of review the unit and talk about what your quiz will look like. All right. So I hope this video helps. Have a great day.